Hello students, welcome back. Let us resume our discussion in section 4. Entire section 4 must have been an optional section for most of the students, but Theorem 4.1 and its consequence, Theorem 4.3, were a little bit manageable, so I hope many students, maybe not majority, but close to majority of the students got it done. Now let's go to harder type of problem. It's this: the multiplicative property of the determinant. Determinant of the product is the same as the product of the determinants. How do we prove it? We're going to prove it in multi-step. Number one, we will prove it for upper triangular matrices. For these kind of special matrices, where we have some non-zero entries and upper right-hand side corner, but lower left-hand side corner, we have to have all zero. These kind of matrices are called upper triangular matrices. And vice versa, if you have non-zero over there and top, upper right, those are all zero, then we call them lower triangular matrices. I can do the same thing for lower triangular matrices, but traditionally, it is more convenient to use upper triangular matrices. I don't know whether it's more convenient, excuse me, I take it back. In terms of convenience of the techniques, they are pushed, they're the same. But traditionally, people use upper triangular matrices. Okay, all right. Let's do this. Let's calculate the determinant of A. How do we do that? First number times the determinant of this deleted matrix, and then all these columns, they're all zero, so they all disappear. So I only have A11 and this determinant. How about this determinant? We have A22, and then, all zero, so we have A22 times this determinant. See the pattern? A33 and all zero, so what's left? This deleted matrix. And this just continues on. So what's the conclusion? Determinant of A should be the product of all those diagonal entries, which are highlighted in blue. See those? How about B? Same thing. This and then all zero times determinant of that, and this is B22 and all zero times determinant of this, and B33 times and so on and so forth. So we have to have this product of all the diagonal entries. Same for A times B. A times B, I have to talk about it. Sorry about that. A times B, how do we calculate A times B? First row times first column, what do you get? A11 times B11. Everything else, they're all gone by these zeros. So we have A11 times B11. How about this one? First row, second column, you're going to get something. First row, third column, you're going to get something, all those. I don't care too much about those. Now let's go to second row, first column. So 0 times B11, so that disappears. And all these non-zero numbers times all these zeros. So what do you get? We have 0. Next, second row, second column. B12 times 0 and B22 times A22. Okay, that's good. But how about all these? They're all zeros. So what do we get? A22 times B22, the product of the diagonal entries. And then, how about second row, third column, fourth column, and so on? We're going to get something. I don't care. Now, how about the third row? Third row, first column. 0 times B11, that's 0. And, all 0, so we have to have 0. How about second row? Third row, second column. These two zeros kill off these two non-zeros, and all these non-zeros are annihilated by these zeros. So what do you get? 0 again. You see the pattern? Third row, third column. These two non-zeros are killed by these zeros, and all these non-zeros are killed by these zeros. What do we have? Just A33 times B33. And then I may have something. In short, upper triangular times another upper triangular must be upper triangular. So upper triangular matrices, the set of all the upper triangular matrices are closed under multiplication. And then, furthermore, the diagonal entries are just product of each diagonal entry. A11 times B11, A22 times B22, A33 times B33, and so on. Oh, that's really helpful because if you calculate the determinant of this upper triangular matrix C, which is A times B, this is what you're going to get. A11 times B11, A22 times B22, and so on and so forth, all the way over to ANN times BNN. Now, multiplication is commutative, so we can rearrange those multiplication. Then we have all the A's here times all the B's. Conclusion, determinant of A times determinant of B. So what's the conclusion? If we have the product of two upper triangular matrices, then this multiplicative property holds. So that is the conclusion from step 1. Now, is this going to be useful? Oh, yes, it will be. Why? Because it is possible to make any arbitrary square matrix into an upper triangular matrix through elementary row operations or elementary column operations. Actually, we can do both. And there's a name for those kind of matrices. In chapter 3, we used to call them row-reduced or column-reduced echelon matrices. Remember? Row-reduced echelon matrix or column-reduced echelon matrices. Those are upper triangular, and if you're interested or if you forgot about all those, then you can go back and open up this module 3, maybe module 4, and then restudy those. Okay, now we talked about elementary row operations. Okay, let's talk about those elementary row operations. There are 3 types of elementary row operation: multiplying a non-zero number to a row, switching 2 rows, and third, adding 1 row to another. Actually, multiplying a scalar adding it to another. Okay. Multiplying a scalar to 1 row and then adding it to another. And that's a good way to remove a certain entry and make it into 0. And we used to do all kind of things. Okay, all right. Here's the first elementary row operation, multiplying a non-zero number. So multiply C to entire row. And what is that elementary row operation matrix? It looks like this. Just C on ith row and everything else just 1 in diagonal. We start from the identity matrix and then just take this C. And then we multiply, and then indeed we have this multiplication in this row. Now, what is this determinant of A? Well, that determinant is C because we have to multiply all those diagonal entries, and they're all 1s except for this C, so this determinant is C. How about determinant of A times B? Well, we have this C multiplied into entire ith row, so we can use the multilinear property and take out this scalar multiplication. So C times determinant of B. So what's the conclusion? Determinant of A times B is C times determinant of B And C is equal to determinant of A, as you saw here. So what do you get? Determinant of A times B is equal to determinant of A times determinant of B. Yes, it works for first elementary row operation. And by the way, it'll work for elementary column operation as well, because this very matrix here is going to be an elementary column operation matrix if you multiply to the right. So each matrix here does double duty, as a matter of fact. Elementary row operation matrix and elementary column operation matrix, actually they are the same. One applies to the left and the other applies to the right. Anyway, okay. Second, switching two rows. And here, if we switch these two columns, I and j, and then multiply to the left, and that's what makes this bij and bi and bj switched over. How about this determinant? It is -1 by the alternating property. We have ith here and jth here, then that's identity matrix, so that determinant is 1, and we switch these two columns. So determinant of this elementary row operation matrix is -1, excuse me. And if you apply this elementary row operation, then what do you get? Switching these two rows, so we have to have negative of the determinant. And then put those together here. Determinant of AB is, as you've seen here, negative of determinant of B by this alternating property, or equivalent to -1 times the determinant of B. But what is the -1? That's determinant of A. As you saw here, determinant of A is -1. So yes, we have what we want. Determinant of the product is a product of the determinant. We got this property for now 2 of 3 elementary row operation matrices. Oh, by the way, if you multiply this to the right-hand side, instead of AB, if you do BA, then it is the corresponding elementary column operation. So each matrix actually does a double duty. The reason each elementary matrices does a double duty is because we are dealing with these square matrices. If they are not square matrices, then they are different. In chapter 3, we did arbitrary matrices, so things were different. Here, everything is square matrix, we are doing determinants, so everything is just doing double duty. Okay, next. Multiplying a scalar to one row and adding it to another, and that's a good way to kill off some number and then making something into 0. And it's this elementary row operation matrix if you multiply to the right. And if you multiply to the left, excuse me, to the right, then it is elementary column operation. Anyway, this determinant is 1. We saw it before. Elementary row operations and elementary column operations. Yes, that determinant stay the same. Stay the same because, oops, excuse me, too much. From the identity matrix, we did this. So determinants stay the same as that of the identity matrix. So save this 1. Now, as for this elementary row operation to matrix B, it's the elementary row operation where taking this jth row and multiply C and adding it to ith row. So that doesn't change any determinant here. We saw that before in 4.4. So if you apply it here, what do you get? Determinant of A times B is just the same as determinant of B, and it is equal to 1 times determinant of B. And what is this 1? Same as determinant of A, as you saw here. So yes, we have multiplicative property. We proved everything for elementary row operation matrices, all 3 types. For elementary column operations, you can do the same thing to the right-hand side, but who'd bother? We'll probably use the column row equivalence, which we proved from theorem 4.1. as far as determinants are concerned, column, row, they're equivalent. And we'll simply go ahead and we have analogous results for elementary column operations as well. Alright, so we are done with steps 1, 2, and 3. So we proved this multiplicative property for upper triangular matrices, in particular elementary row or elementary column, excuse me, what am I talking about? Row reduced or column reduced echelon matrices. And then elementary operations, we are done. Now for the conclusion. Let's begin with arbitrary matrix A, and then let us apply elementary row operation and make it into an row reduced echelon matrix H. So we have multiple steps here, E1, E2, E3 over to EH. And if you use step 2, the multiplicative property for elementary matrices, then we have the product of all these determinants. So determinant of this row-reduced echelon matrix is the same as product of all these determinants. And the last one is the determinant of A. Now, let's apply step 3 to arbitrary matrix B. And this time we used elementary column operations. So we multiply all these matrices, F1, F2, F3, all the way to Fk, all those elementary matrices to the right. And we have column reduced echelon matrix. And that's going to be a upper triangular. So this determinant of K is equal to the product of all these determinants. All these determinants, all those are elementary matrices, elementary column operation matrices. So that's multiplicative from step 3. So we have matrix multiplication here and determinant multiplication there. We have these two properties, blue and green. Now let's combine these two. Let's combine the matrix multiplications first. H times K is equal to this times that, and it comes here. Does it make sense? Alright, next, let's take determinant of H times determinant of K. Multiply this times that, and that's what we see here. So that's determinant of H times determinant of K. Are we there yet? Almost. Almost. Here, which came from this times that, let us take the determinant. Determinant of this H times K is equal to determinant of this, but then again we can use step 2 and step 3. Multiplicative. These are elementary row operation matrices, so multiplicative. These are elementary column operation matrices, so those are multiplicative too. So we have these bunch of determinants here and there. So we use step 2 and step 3 again. Finally, we're going to compare these two. Determinant of H times determinant of K is equal to determinant of H times K because of step 1. We are talking about row and column reduced echelon matrices. Those are upper triangular. So these two are the same. So we have this equality, setting these two equal. Now, do we have some cancellation? Oh yes, all these blue cancel each other out. And all this green cancel each other out. And we get what we want. By the way, do they really cancel each other out? Yes, they are, because these are elementary row operation and column operation matrices, so they're all invertible. So none of them is 0, so we can all divide those out. All those blue and green. So what we get? We have this multiplicative property for arbitrary matrices A and B. Okay, that completes theorem 4.5, the multiplicative property. And 4.6 follows immediately, which I'm going to leave to students. And 4.7, that's going to be covered in a separate video. It's going to be a whole new dimension.